Hello. This lecture will cover pages 189 through 195 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on flip-flops and related devices, Part H, the Monostable Multivibrator. Before we start out on page number 189, I'd like to look back on page 181, talking about timing circuits. We said we'd discuss three types of timing circuits: the bistable multivibrator, which was stable in two different states. They were called flip-flops. The astable multivibrator, which were the free-running oscillators, they were stable in neither state. They switched back and forth. The final type of timing circuit we're going to look at is the monostable multivibrator, also called one-shots, OS for short. Monostable multivibrators are a digital circuit that is somewhat related to the flip-flop. Like the flip-flop, the one-shot has two outputs, Q and Q bar, which are the inverse of each other. Unlike the flip-flop, the one-shot has only one stable output state, which is normally Q being 0, where it remains until a trigger is applied as an input signal. Once the trigger is applied, the output switches to the opposite unstable state, Q equal 1, for a certain period of time, T sub P. And after that TCP, the time pulse, has elapsed, it returns back to its stable state. So we're going to start out by looking at page 189 in your lecture notes, keeping in mind that the monostable multivibrator has many different applications. It can be used as a frequency detection circuit. You'll see that in your homework. It can be used for delay intermittent windshield wipers on your automobile, to basically set the time the windshield wiper delay is going to run and then stop. A delay of a security spotlight in a driveway. Whenever it sees motion, your spotlight comes on, it stays on for a certain period of time, and then it goes off until it sees motion again, and it goes on for another minute or 2 minutes. You set that by a potentiometer up close to the light. Or clock gating. That's just 4 examples of how you can use it, and I think you'll see it as we continue to go through the lecture. On page 189, the monostable or one-shot circuits are only stable in one state. But if an external signal or a trigger is applied, they change to its unstable state for a fixed period of time, and then after that T sub P time period, they return back to their stable state. This is the basic block diagram of a one-shot. Notice as I'm showing as a positive edge triggered, they come negative edge triggered, but here we're going to look at a positive edge triggered. The trigger comes, and the output is going to go for its stable state to its unstable state for a certain period of time, and then it's going to go back to 0. There are two basic types of one-shots. There are non-retriggerable one-shots and there are retriggerable one-shots, and we're going to look at both of the two different types here. First of all, what do we mean by a non-retriggerable one-shot? In a non-retriggerable one-shot circuit, you have to look at this block diagram up above. The positive edge triggered comes and the Q output goes high. It goes high for a certain period of time and then it goes back to its stable state. If the trigger comes again, the output again goes high. It's unstable at that point for T sub P, and it goes back low again. You'll see how we can change this T sub P time, this pulse width, very shortly. The non-retriggerable one-shot won't retrigger if it sees another positive trigger during that T sub P output pulse. In other words, if you take a look down here, what they're trying to show you is that the trigger goes high, it produces this T sub P pulse. But during this T sub P output, it's already in an unstable state. Another trigger comes. It doesn't extend this out to here. It ignores this positive edge triggered if it's within the time T sub P. That's called a non-retriggerable one-shot. Compare that to a retriggerable one-shot, which looks like this. At T sub 1, you get a positive edge triggered, and it fires T sub P, and you get a T sub P pulse here. And normally it's going to go away at that point. The output goes away, but you get another T sub 2. Well, let's take a look. I'm looking at this wrong. You get a T sub 1, and here's your T sub P. Your T sub P is 1, 2, 3, 4, 5, 6, 7 divisions. I have it laid out here as 7 divisions. But you get another, at T sub 2, you get another trigger. So it's going to extend this. It's going to re-trigger this another 1, 2, 3, 4, 5, 6, 7 of these blocks. See how it extends this T sub P pulse. Normally, that's going to go low right here. If it's a non-retriggerable one-shot, it's going to go low right there. But if it's going to stay low. But since it's retriggerable means a new T sub P at time T2. It extends the pulse if a trigger occurs within T sub P. They do a pretty good job of this in your textbook, looking at a couple different figures here. First of all, let's take a look at this figure here. Notice that here we have a positive edge triggered one shot. This is normally low. We're not going to worry about the Q bar output. This is normally low. Obviously, this is going to be normally high. Notice there's a value of R and there's a value of C. That's going to determine your pulse width. The pulse width is proportional to the product of R times T, of the one resistor and one capacitor. You only have 2 of these elements to deal with in this circuit. So notice down here, it's a non-retriggerable one-shot. You get a trigger, you get a pulse width. You get another trigger, you get a pulse width. Over here, you get a trigger, and you get a pulse width. And this pulse D occurs within this pulse width, so D is ignored. Then you get another trigger on E, and F occurs within that pulse width, so both D and F pulses are ignored up here. Let's take a look at the next page. You do a pretty good job on this, and I want you to notice that this is how a non-retriggerable works here. And this is how a retriggerable would work, and here's the pulse. Here's the positive edges of a trigger. Non-retriggerable and retriggerable. They're talking about a 2 millisecond interval here. T sub P is a 2 millisecond interval. So you can see here that here's time down below here. So you get a trigger here. This fires for 2 milliseconds. 1, 2. You get a trigger at 1 millisecond. This goes to 3 milliseconds. It goes away. You get another trigger. This is normally going to go out here to 2 milliseconds. It's going to go out to here. Notice that that's ignored. And this goes away. But in a retriggerable one shot, if you look at retriggerable, this isn't going to be ignored. It's going to extend this 2 more milliseconds. Non-retriggerable output, retriggerable output. And they explain this down here. If you take a look down here, you can see that they explain the same thing down here as a non-retriggerable. It extends it 2 milliseconds. And you can see that right here. You get a positive edge, it extends this out 2 more milliseconds. It keeps extending the pulse width. Configuring the 555 timer IC as a monostable device, pretty easy to do. It's on page 191. Down at the bottom it says you might want to get out your 555 specifications, your spec sheet for the 555. I think it's on page 7 or 8. Talks about the application notes, the monostable operation of this. Discusses the astable and the monostable. I think the monostable's first though. Notice that the configuration is you have a resistor. Let's make it a fixed resistor now, not a variable resistor. It's a fixed resistor and a fixed capacitance. And this pulse output is given by the formula here at the bottom. T sub P is approximately equal to 1.1 times the value of R times the value of C. So what happens is these 555 timers are non-retriggerable one-shots. They're only configured as non-retriggerable one-shots. So if you look, they're negative edge triggered devices as well, not positive edge triggered devices. So when this trigger goes low, it fires the output pulse, goes high. So the output is in a stable state until the trigger comes. Once that trigger comes, the output fires T sub P, which is given by this equation down here. It's a function of the values of R and the value of C. It stays unstable during that time, and then the output goes low. Goes back to a stable state. Like I said, this is used in many different applications. When you configure this, notice pin 7, pin 6 and 7 are shorted. Pin 8 is VCC, pin 1 is ground. Here's your stabilization 0.01 microfarad capacitor to pin 5. There's not 3 resistors to deal with. There's 1 resistor and 1 capacitor. Pretty easy to use. On page 92, I might want to mention here that, remember I said you could use this in a couple different applications as, whenever you see motion, you might want to keep the spotlight on a little longer, or if it's raining a little lighter, you might want to cut back on the pulse width and not run the windshield wipers quite as long. All you have to do to vary this pulse width right here, because this is going to drive a transistor or a solenoid or a relay to drive the motor of the motor that drives the windshield wipers, or to turn on the light. There's other circuitry out here, obviously, but this is the control of it. You just vary this resistor. This resistor becomes a potentiometer. That's why I have it variable here. So by putting a potentiometer here, as you vary this resistor, you make this resistor larger. It's directly proportional to the time. You make that resistor larger, this pulse gets longer, this stays on a little longer. You make that resistance smaller by cranking the pot in another direction. Notice that you reduce the time that the windshield wipers are on or the spotlight's on. You have control over that in your circuitry by making this a variable resistor. Clock gating. On page 192, I want to show you how you can use a 555 timer in a monostable circuit for clock gating. You can read the definition of clock gating up here, stop the video and read it, but basically whenever you're running many clocks continuously through a flip-flop, uses lots of power. So you might want to gate just certain amount of clocks. You only want to use certain amount of clocks and turn them off when you don't need them. Well, if you notice here, what we're going to do is set up a one-shot multivibrator here. A monostable multivibrator is a one-shot with a T sub P of 45 milliseconds. You could pick values of R and C to give you 45 milliseconds. It's non-retriggerable, don't forget. And out here you have an asynchronous signal that when the clock comes, it just basically provides a trigger to the one-shot, and you enable the pulse. This is a pulse-enable circuit that enables this clock through this AND gate. When this goes high, clocks can come through. When this goes away, the clocks go away. So here you get your external signal, asynchronous signal at this point. And we're going to gate so many of these clocks through. How are we going to do it? Well, we set this up as 45 milliseconds. The clock period is 15 milliseconds. There's 15 milliseconds between the clocks here. So when the trigger comes, you fire T sub P at 45 milliseconds. Your pulse enables 45 milliseconds, so you're going to allow 3 of these through. You're going to allow 3 15 millisecond periods through that 45 millisecond. So all you see out here is gated clocks, 3 clocks. Has many applications. We won't go into them now, but if you ever need a clock gating circuit, that's useful. And then finally, on page 193, I want to mention something called clock skew. This has nothing to do with the monostable multivibrator, but it's something they talk about in the book. It's in homework problem 552. So I'm going to mention something about clock skew. Clock skew is a common timing problem when designing synchronous digital circuits, and I'm going to demonstrate it here, how it manifests itself. Notice that, let's see if we can get this all on here. I think we can right there. Notice that up here we have 2 D flip-flops. And when the first clock comes here, when this clock goes high, nothing's going to happen in the circuit. because these are low active D flip-flops. And what we're going to do is delay this 1 by 1 clock period. When this goes low, the 1 goes to here. When this goes low, that 1 goes to here. So initially, when the first, this is a low and that's a low. Q1's low and Q2 is low. Well, what happens if you look at the timing diagram, and I put the propagation times low to high and high to low, I put them on here so you can see what's happening. But basically, whenever this clock edge comes, this output here, Q1, goes high through a propagation time low to high. Low to high on this, the propagation time it takes that 1 to propagate through to here. Well, that 1 gets out here before this clock edge gets through. This clock, there's a clock skew between here and here. When this clock edge goes low, this clock edge doesn't go low right away. Clock 2 can't follow clock 1 directly because it has to propagate through this NAND gate and this inverter. Now, the reason I have these two in here on the design is that I want this phase of this clock to be in the same phase as this, but this is just an enable that allows this to come through, but it comes through with an inversion. So I just have to put another inverter here to negate that bubble on the NAND gate, so that when this has gone low, this has gone low. But there's clock skew because this doesn't go low the same time that goes low. Clock 1 goes low here and clock 2 goes low here because there's this clock skew. And the reason there's a clock skew down here at the bottom, you can see that it's the propagation time of this NAND gate plus the propagation time of the inverter. So what happens is that this 1 beats the clock edge here, and this output Q2 goes to a 1. All because of that clock skew. We have to slow this signal down up here. We can't let Q1 to get set up and then sometimes later, because of this clock skew, this negative edge on this clock finally makes it out here and it sees that 1 and this goes to a 1 when that goes to a 1 during the same clock period. So what you do to solve that problem, if you look on page 194, to prevent this from happening, you try to minimize the clock skew in your design. You can minimize the clock skew in your design by using faster gates down here, but sometimes that, get some high-speed CMOS or some ALS, advanced low-power Schottky or Schottky devices here. AS, advanced Schottky devices, might speed it up a little bit. But another way you can do it is you can delay the time it takes Q1's output to reach D2's input. In other words, on the output of Q1, between Q1 output and D2 input, I put 2 inverters here. Why? Well, if you go back and take a look at the circuit, the reason I put 2 in is one compensates for the delay here, another one compensates for the delay there. The propagation time of an inverter is roughly the propagation time of a NAND gate. You can look it up. So if I go up here and I put 2 inverters in, it'll slow this 1 down so that it won't set up here. It won't be already set up when this clock edge comes. So what will happen is you get the first edge, 1 goes to here, and this will stay at 0. And then on the next clock edge, this will go to a 1. So you can negate that clock skew by putting 2 inverters in series up here to basically equal the propagation time you have down here of the clock 1 to clock 2. That concludes this lecture.